play really a pivotal role in theory of geometry, especially when you are doing geometry on manifolds, when you are doing differential geometry on manifolds actually. And hence that's what makes it important in the general theory of relativity. Okay? Not only general theory of relativity, but also in quantum mechanics actually, because in order to do the general theory of relativity, the language of general theory of relativity is differential geometry, and the differential geometry most of the time depends on functionals actually. Okay, and even special. If you, for example, you talk about special theory of relativity, the special theory of relativity is basically done in a product space, not in a product space. It's kind of a pseudo inner product space, which kind of assume that our space is a four-dimensional manifold actually. So it's a four-dimensional inner product space in which you do the entire special theory of relativity. Okay, and it is a beautiful theory developed by what do you call the Einstein. So what we can see from all this, that the mathematics that you are learning, the linear algebra that you are learning, is almost like a language actually. So in which you can write a lot of practical things in that language. Okay, for example, the physicist has been doing it all the time actually. Okay, what would be some other example? Let's do some other example. So this is one example, and you can treat this as really as an example of the example, because this is a generic example. I just use a concrete inner product space and a concrete inner product and a constructed an example. So we kind of saw actually that this is the inner product is this integral is a linear functional. So you can also show actually that if you have a derivative evaluated at a point, or you have a gradient evaluated at a point actually, you can also treat that as a linear functional actually. So for example, you take a function, you compute its derivative. So the function is from some space, for example C1 class, and by C1 class I mean the space of differentiable functions, and do the evaluation of the differentiable function or the derivative of a differentiable function at some point. Now obviously it's going to spit out a number actually. So it's going to be a map from space of differentiable functions into the numbers, and hence differentiation at a point is also an example of linear functional. So there are plenty of examples. You're going to encounter a lot linear functionals in your future. For example, another example that could be maybe you can verify it for yourself, that you take the space of continuous functions over 0 to 1 and you define a phi from V into R. So phi from V into R by phi is a map that swallows a continuous function, say f, and spits out a number. And the number that I'm assigning here is that take this f and evaluate it at 1/2. Okay, take this f and evaluate it at 1/2. And my claim, or maybe you can verify for yourself, that this phi is also a linear functional. Okay? Now why we are interested in linear functionals? Because now I would like to write what you call the Riesz theorem, which simply says that a linear functional can be classified in a very interesting way actually. Okay, so they could be understood in a very interesting way. Okay. By the way, by definition of linear functional, we kind of saw that for every w in V, I can find a linear functional phi w. But you can go other way around as well actually. You can go other. So if you have a linear functional, you can find a unique vector w such that linear functional can be entirely explained in the terms of what you call w. Okay? So that this is really, in some sense the converse of what we were doing. So here's a theorem, here's a precise statement of the theorem. Okay, this theorem is called the Riesz, R-E-I-R-I-E, as that Riesz representation. Riesz representation theorem. Okay, and it goes like this: that let V be a finite dimensional vector space. Minded that this is also true in infinite dimension. It's also true in more abstract spaces called the Hilbert spaces. Okay, so you have a finite dimensional inner product space. Inner product space over a field F, and let you have a phi that is a map from V into F, and this phi is be a linear functional, be a linear functional. Okay, then here's something interesting that you can do actually. Number one, for every linear functional phi, I can find a unique w in V such that phi of V equal to VW for all V in the product space V. So you have to keep something interesting. So what was the definition? The definition was given W, for the example that we did, example that we did previously, is that given W, I can define a map, I can define a functional corresponding to this W. Okay? That goes like this actually. That goes like this. Now, if you see this statement, what does it say? Take any functional actually. Take any functional. So here it says that this, through inner product, you can define one functional corresponding to each W. What does this statement is telling you? Take any functional, no matter what functional you take actually, you can always find a unique W and you can always write as the inner product of it actually. So every single functional can be written as the inner product, as the inner product with a fixed W. Okay, of any vector B actually. Okay. So you have to be carefully see what is the difference between this and this here actually. Here for every W you can have a functional, and here you're saying that every functional can be written in this form. In other words, for every functional you can always find a unique W such that you can write it in such a form. So every functional is of this form. So if you have any functional, the functional should be of this form. That's it. So this is what makes these representation interesting. And what is the next thing? That in addition, if you know that your inner product space has an orthonormal basis, and we know that it has an orthonormal basis, obviously the interesting question would be that how to find this mysterious W. How to find this mysterious W. So how can I find this mysterious W actually? Okay. So how can I know that for corresponding to phi, what is that W for which I can have this? For which I can have this, for which I can have this, that this functional can be written in this manner. The question is how to find that W. The answer is you can do it very easily. So V is a finite dimensional inner product space. So we know that it must have an orthonormal basis actually. So let's assume that that orthonormal basis is this. So U1, U2, Un actually. And if you have this orthonormal basis, you can construct this W very easily. Then is orthonormal the orthonormal basis for V, then this mysterious W, you can find it easily in the terms of the orthonormal basis, through orthonormal basis actually. Then W in part A can be calculated as what? That the W is going to be take phi of U1. Okay, so the phi is mapped from here to here. So the U1 is a vector here. So phi of U1 is going to be an element in a complex number, and take its conjugate U1. So the W, since W is a vector in V, so it must be a linear combination of U1, U2, Un. So undoubtedly, every single vector here should be a linear combination here. But the question is, what are the coefficients of it actually? So how can I write that W in the terms of U1, U2, Un, and from where I can find the coefficient? The answer is very simple. That then W can be written as phi of U1 conjugate U1, phi of U2 conjugate U2, so on and so forth, and phi of Un conjugate Un. Okay? So if you have been given a definition for the phi, apply it onto each one of U1, U2, Un, calculate their conjugates, and then this mysterious W is going to be this expression actually. This expression. Okay? So it's not difficult. So here, this result, this part tells you that there exists a W using which you can write every single linear functional in the terms of inner product. Okay? Using this W, you can write every single linear functional in the terms of inner product. The question is how to find that W. So here it says that it exists and it must be unique, but it doesn't tell us that what is it. So the answer is that if you take this W, it really, satisfies this condition actually. In other words, your W must be this. So here's a proof for it. Here's a proof for it. Okay. Here's a proof for it. So take a vector V from the inner product space V and and write it in terms, okay, let me say, and orthonormal basis, u1, u2 up to un for it. Okay, u1, u2, un for it. And u orthonormal basis u1, u2, un. Then I know that I can write this v in the terms of these u. So what I would like to do, I want to compute this, and I want to compute that phi of v in such a form. And then I want to know that what is that w. So take phi, which is an arbitrary linear functional, and operate onto v. But the v being a vector in a product space, v can be written as the combination of this. So let's write this as a linear combination I equal to 1 to n ui. Okay? And remember what would be the coefficients when you try to write the v in the terms of an orthonormal basis. The coefficients are very simple. We don't need to write them abstractly. They are going to be v, ui, ui. So this is what that we did in the last session actually. That if you have a vector and orthonormal basis, finding coefficients is not a big deal. Just take the inner product of v with each of the ui and multiply with ui. So that will be the combination. Now phi is what? Is a linear transformation. So if phi is a linear transformation and this is a scalar, then we know very well that phi can be written, then phi preserves the addition in scalar multiplication. In other words, phi of the sum is going to be equal to the sum of the phi. So it's going to be phi of v ui ui. Okay, this is what it is going to be. Now this is in scalar in the field f, so I can pull this out of the phi I equal to 1 to n. So it's going to be v ui times phi of ui. Okay, this is what that you're going to get. Now, by the way, what is phi of ui? Phi is a map from v into f. So ui is a vector here, so phi of ui is a number actually. So it's a number. Okay? It's a number. So if I take this number and multiply it with, for example, this second component, okay? If I take this number and multiply it with the second component, what it would become actually. So the phi of v will become v times phi of ui conjugate. We need to conjugate it. Ui. Why you need to conjugate it? Because if you pull this out, this will become the conjugate of the conjugate, which will become phi of ui. And the sum I equal to 1 to n. Okay? And then, if I wish, I can take this sum inside actually. Okay? So the sum of the second components, I can write it as the inner product of v with the sum actually. Okay? So I'm assuming that you know the such properties actually. So I equal to 1 to n phi of ui bar and ui. Okay? Phi of v. Now give this guy, so let's call this I equal to 1 to n phi of ui bar ui, call this w, or give it a name w actually. Okay. Give it a name w. Hence, if you give this guy a name w, so the phi of v is going to be vw for all v in v. And I know that my w is this. So the most of the things in part A and part has been proved actually. So we proved kind of existence such that phi of v can be written in such a form. And the second thing that we proved is that this w must be of this form. The only thing that remains is really the uniqueness actually, that why such a w should be unique. So to prove the uniqueness, let us assume, okay, so the uniqueness, let us assume that I have a y, another y in V such that phi of V is equal to Vy for all V in V. Okay, this is what is going to happen. Now, since phi of V is this and phi of V is this, so these two should be equal. So you're going to have a V W equal to V Y, and this means that I can take this guy here and I can write this as V W minus Y equal to 0, and for all V, Now, this means that this vector W minus Y is orthogonal to every single vector V in the inner product space. Now, can you tell me that what is the vector which is orthogonal to every single vector in the inner product space? So, I mean, if you remember chapter 4, we proved actually that the only vector which is orthogonal to every single vector in what do you call the inner product space is 0. So if W minus Y is orthogonal to every single vector V in the inner product space, then W minus Y must be 0, and hence W must be equal to Y. So what does this show? That if you have another Y that satisfies this, that is same as W. So you can't have two such representations. So this kind of shows uniqueness actually. Okay, this kind of shows the uniqueness. And this result is what you call the Riesz Representation Theorem. So the Riesz Representation Theorem is one of the most powerful theorem in finite dimensional analysis, in infinite dimensional analysis, and for example, being a person who is very much interested in the theory of differential equations, partial differential equation, and stochastic differential equations, we quite often use, what do you call, Riesz Representation Theorem in our PDE theory to show the existence and uniqueness of the solutions to our problem actually. Okay? Just the existence and uniqueness of solution to our, what do you call, the problems. Okay, so it's a very useful theorem. So once again, what does this theorem say? Take any finite dimensional vector space, inner product space, and take any linear functional. Then every single linear functional can be written in this manner. In other words, for this linear functional, you can always find a unique W, so that that linear functional can be expressed in the terms of inner product. So no matter what is the definition of phi of V, doesn't matter, you can always turn it into what you call the form of inner product. And this mysterious W that you need to write the functional in the terms of inner product is basically this W. So you can calculate it easily. Okay, so here's a definition, and maybe I can do one example. Of this. So definition is this: for phi from V to F, I know that I can find a unique W. So this W that is uniquely associated with phi, you call that W as a Riesz vector. So this W is called Riesz vector. Okay, so this vector has been given a name. Okay. Now here's one example. Consider vector space to be Mn. Okay, the space of n by n matrices with Frobenius inner product. So we discussed what is the Frobenius inner product on n by n matrices. So you have to do it for, you have to recall it for yourself. And then let me define, for example, a linear functional that swallows a matrix from Mn and spits out a number, say R. Okay? R, maybe R, C, doesn't matter. You can have anything. And you define that phi of A as the trace of A. Okay? And we know that what is the meaning of trace for n by n matrix? So just sum the diagonal entries. Okay, so the trace is the sum of the diagonal entries of A actually. So A is an element in this inner product space, and trace of A is a number, could be complex number, could be real number, and we can prove that this is a linear functional. It's not a big deal that this is a linear functional. The question is, what is the Riesz vector for the trace? What is the Riesz vector for the trace actually? Okay. By the way, shall I recall that what is the meaning of Frobenius norm from this inner product? So Mn is the collection of n by n matrix. Okay, so everyone knows Mn. The norm on Mn, that if you take matrices A, B, and it's the Frobenius inner product. Okay, then this is equal to conjugate of B multiplied with A. So this is what the definition of the Frobenius inner product is. So we proved in the chapter 4 that this becomes an inner product space. Now, my claim is that the Riesz vector here is the identity matrix actually. For this functional, trace functional, the Riesz vector is identity matrix. How? Because phi of A is a trace of A, but I can write the trace of A as I star times A, because I star is I, okay, undoubtedly. Just go back and check out. And by definition this, no, shouldn't be B star A, but the trace of B star is on this. This is what it should be. So if you have a definition, trace of I star A, so by the Frobenius inner product, this is going to be A inner product with I in F. And this is true for all A in Mn actually. So what does this shows? For the trace functional, the Riesz vector is the identity matrix actually.